Спасибо.
Наш следующий докладчик проделал длинный путь, чтобы сюда прибыть, что особенно сложно в наше время, и это особенно ценно. Он представляет сразу и Турцию, и Кипр, и Туркменистан. От себя добавлю, что еще много учился в моем родном Воронеже. Это прекрасно нам известный всему миру тоже Allaberen Ashyralyev. Я объявлю тему доклада по-русски, а докладчик выберет сам, на каком языке ему докладывать. Итак, о корректности нелокальной краевой задачи с условием Самарского Ионкина для эллиптических дифференциальных уравнений. Прошу, 45 минут.
Как будет контакт? А? Вот так, да? А вот так? Нормально? Что теперь? Ага. Вот так, да? Наверное, прежде всего, мне разрешите поздравить дорогого нашего Александра Леонидовича юбилея. И мне приятно находиться и быть среди окружения Александра Леонидовича. Мне действительно вот помнится, как я встретился с Александром Леонидовичем. Сразу он руку подал, помогал мне. И действительно, быть ученым – это одно. Еще надо быть, как бы сказать, человек, которого может видеть, у кого есть нужды. В тот момент у меня был очень такой трудный момент. В 2016 году после пенсии почти я безработный был. И, значит, предложение Александра Леонидовича было очень прекрасно для меня, для поддержки. И я, Александра Леонидовича, самое главное, я увидел, вот откуда исход энергии, прекрасного ученого. Прекрасные ученые, мне так кажется, они не становятся, они рождаются. И прекрасных учителей всегда проблема. Вот прекрасные ребята, которые помогают, оттуда идет энергия, мне кажется, большой. И, значит, я рад, что я встретился такого человека, именно прекрасного ученого. Одно мое пожелание – здоровья. Берегите себя, потому что вам нуждается молодежь, действительно, и окружение ваши, друзья. Я немножко младше, поэтому как старшего брата обращаюсь и прошу. И мне еще раз вот хочу отмечать, мне было приятно находиться здесь всегда, и оттуда энергия возвращаясь домой. И, значит, как вот Андрей сказал, на каком языке сам выберет. Да, я могу, конечно, по-русски выступить, но у меня не всегда будет так хорошо, потому что я готовился на английском, думал, что это RUDN. Все будут выступать на английском. Ну, если что-то я перейду, может быть. А? Да, быстрее будет, потому что когда вот я помню, Ташкенте выступал по-русски первый раз 20 лет Шейхата Алимовича юбилея. И действительно, я не успел ничего. Половину я не рассказал. So, first of all, I would like great thanks to say great thanks organizing committee for invitation me in this conference dedicated 70th years. Professor Alexander Skubachevsky. The title of my talk today on the non-local boundary problem with Samarskii Ionkin condition for the elliptic differential equation. Okay, but you can meet with such, must be closely subject, many papers. and different people interested with this problem, and starting point was paper, Elena and Samarskii. Today, my talk also about it. So I will consider elliptic problem with Samarskii Ionkin condition in Banach space with positive operator. So here main theorems of well-posedness, this problem are established, and in practice, I would like to consider here new course stability estimates for this solution 5 simpler type of non-local boundary problems with Samarskii condition for differential equations. So outline my talk, introduction, auxiliary results, main theorems on well-posedness of the non-local boundary problems, Samarskii condition, and later applications. Finally, I will here give some conclusion and about my future plans. Elliptic differential equations have applications in almost all areas of mathematics, from harmonic analysis to geometry to Lie theory, as well as numerous applications in physics and engineering. The well-posedness of the local boundary value problem for elliptic equation, one in arbitrary Banach space with positive operator, and its relative applications have been investigated by many research. I give here only 4 references, but maybe more, but this is classical books, monographs in this area. So in mathematical modeling, elliptic equation are used together with local boundary condition specifying the solution on the boundary of the domain. In some cases, classical boundary condition cannot describe process of phenomenon precisely. Therefore, mathematical models of various physical, chemical, biological, environment process often involve non-classical conditions. Such conditions usually are identified as non-local boundary condition and reflecting situation when the data of the domain boundary cannot measure directly, or when the data of the boundary depended on the data inside of domain. The well-posedness of various non-local boundary problem for partial differential and difference equation has been studied extensively by many researchers. So only some reference I try get maybe different region names, papers. The server paper 35 contains the results on the local and non-local well-posed problems, second-order differential and difference equations. Results of the stability differential problem for second-order equations, differential and difference equations, and also difference schemes for approximate solutions, second-order problems presented our joint paper here, server paper, but also we will consider here several type applications, well-posedness, well-posedness, elliptic problem, and also hyperbolic problems here as applications. In the paper 36, Ionkin studied non-local problem for one-dimensional parabolic equation arising in modeling some non-classical thermal processes. The existence of solution was proved, and later the stability was established 37. For parabolic equation, one space variable, Samarskii 38 proposed a non-local boundary problem formulation covering both classical initial boundary problems and Ionkin problems from 36-37. Recently, various non-local boundary problems with Samarskii condition for partial differential equation have been investigated by many researchers. In these references, also here, many references, I concentrate some paper, not maybe full. In present paper, in Banach space E, non-local boundary problem with Samarskii Ionkin condition for elliptic equation, one with positive operator is considered. If you put here mu equals 0, it is maybe very well problem for study, because here differential operator, if you consider operator space if you consider here second order operator with mu equals 0 and C equals 0 conditions, here we have self-adjointness and positivity. But here problem when mu greater than 0. And this is reference now. A function U of t is called solution of problem 2 if the following condition satisfied. U of t twist continuously differential on the interval 0t and continuously differential on the segment 0t. Element ut belongs domain of A, and the function A of t must be continuous, and U of t satisfies equation and non-local problems. In the present paper, we study well-posedness of the problem, non-local problem 2. Throughout the paper, the main theorems on the well-posedness of non-local boundary problem are established. Applications in new coercive stability space for solution 5 types of problems elliptic equation are obtained. We need some auxiliary results. Start with positivity, but here we consider Banach space, so we need positivity property of operator, and this is a very well-known definition. The operator A is said the positive if spectrum sigma of A lies interior of sector of angle. On the side, these edges, C1, C2, and outside, it is resolvent, is subject so bounded, so estimate 3 satisfied. So the infimum of all such angles is called the spectral angle of positive operator A, and it is denoted by phi of A. It is dependent with operator and spaces E. The operator A is said strongly positive in Banach space if a spectral angle less than pi over 2. The operator square root of A has better spectral property of positive operator A. Indeed, the operator minus A minus square root of A generate analytic semigroups exponential minus TB when t greater than 0 with exponential decreasing norms. So we have estimate for such type estimated, and from that follows 1 minus exponential minus TB bounded and inverse R, and for R we have estimate 7, and the following formula 6 holds for exact solution of problem 1 and the sufficiently smooth data where 0 where of t and of t. Now we will introduce some spaces. First, we denoted by sigma alpha E of the Banach space obtained by completion of the set of all smooth E-valid functions on the 0t in this in the norm. As you see here, Hölder space without weight, and we have the following results. Suppose second derivative at the point 0 and t from some interpolation space. Later we will define it, E alpha, f of t, right side from Gölder, then boundary value problem 1 ill-posed, well-posed in Gölder space C alpha, if A is positive operating in Banach space. For solution of t in C alpha, the following coercive inequality holds 7. Here, Banach space E alpha generated by E and domain of square root of A, and consists all whose were from E, which norm, this norm is finite. Moreover, the positivity of A is a necessary condition well-posedness problem 1 in C of E. However, the problem 1 is not well-posed in C for all positive operators. It turns out the Banach space E can be restricted to a Banach space E prime from domain of A to E, in which manner that restrict problem 1 in C prime will be well-posed in C E prime. The role E prime will be played the fractional spaces, interpolation space E alpha. So we have theorem 2.2, let A positive operating Banach space E and f of t from C E alpha, then the solution of t in C alpha, the following coercive inequality holds 8. We have such type coercive inequality in C E alpha. So now main theorems on the well-posedness of the non-local boundary value problem is Samarskii condition. First of all, we will give some lemma. Let a positive operator Banach space E, then operator in this parenthesis has an inverse P, and the following estimates holders 9 and 10. The proof of lem 3.1 is based on the positivity of operator in Banach space E, and on and also estimates 4. We consider non-local boundary problem 2. Using formula, first condition U0 equal phi, we can get formula for solution U of t 11, but here unknown right side U of t. Now taking derivative, we can find second order derivative, and using now Ionkin condition, Samarskii condition, we have some relation for U of t unknown, but as you see, U of t here acting two operator product. Both one has inverse. First one follows from strong positivity of B and mu positive. Second one follows from lemma to 1. And so we have formula for U of t, and it is easy to show that U of t defined on the derivative by formulas 11 and 13 is a unique solution of C of E of the problem 2 if the example, when we smoothen data, I put here, sufficient condition for the well-posedness of the non-local boundary problem 2 can be established if one considers this problem in certain space of E-valid function defined on the derivative. Note the solution of problem 2, coercive inequality in Hölder space without weight fails. Nevertheless, we have results, theorem 3.1. Suppose xc plus mu f of t from space E, A phi minus f0 belongs to interpolation space E alpha. Right side f of t Hilbert space. Then boundary problem 2 is well-posed in Hilbert space, C alpha of E, if A is a positive operating Banach space. For solution U of T in C alpha, the following positive inequality holds. And here, proof based on the theorem 2.1, and we must get estimate AU0 my F0U, but it is F phi minus F0. So we have estimate, but really we need estimate A of T minus F of T norm E alpha. So first we will write formula for this element, and now using estimates 9 for 10 and definition of Hilbert space and E alpha, we can get estimate 15, and theorem 3.1 prove it. Second, one can enrich family of spaces smooth functions in which the boundary problem 2 is well posed by introducing the spaces C beta gamma of E, and above we denote 0 and T. So this is obtained by completion of set of smooth E-valid function phi of T with respect norm. As you see here, we have two weight T plus tau at the point 0, gamma, and T minus T gamma, and tau beta. Here beta greater than equal gamma. By the way, usually such type norm introduced first time I see Samarskii paper, 1969 paper, when beta and gamma equal 0, Samarskii used weight T gamma and T minus T tau gamma. But really it is equivalent when beta and equal gamma. But in general case, it is not equivalent, and we have here well-posedness results really in these spaces, but not other one. So assume that A is a positive operating Banach space and a C minus mu F of T from E and a phi minus F0 from intersection of interpolation space and space of faces. Later also I will introduce second E alpha beta F of T from Hilbert space with weight. Then we have the following results. For the solution of T in C beta gamma of E, boundary problem to the corresponding inequalities holds. So we have corresponding inequality. Here norm omega beta denotes norms of Banach space E 0 beta consists of whose omega from E for which norm is finite. This is spaces of faces. Note the parameter gamma can be chosen freely from 0 to beta, which increases the number of function spaces in which non-local boundary problem 2 is well posed. In particular, theorem 3.2 implies the well-posedness theorem 3.1 in Hilbert space C alpha of E without weight established before. Theorem 3.3 suppose a positive operating Banach space and a phi from E, a C from E, a phi from E interpolation space E alpha, right side from C of E alpha. Then for the solution of T in C of E alpha, the boundary problem corresponding inequality holds. So here briefly proof, we will prove using by theorem 2 and also estimate A of t. We have formula of E of t, and using now estimates 9, 4, 10, and definition E alpha, we get 16. So third, let us study now boundary problem 2 in the spaces C beta gamma, but of E alpha minus beta. We introduce now spaces 3 index, alpha, beta, gamma. Why later we will see. To this here corresponding spaces trace E alpha, beta, gamma, alpha minus B, which consists of elements omega from E for which the norm is finite. And we have now the following 2 theorems. Let A is a positive operator Banach space and some condition for data. And then we have stability inequality in C beta omega of E alpha minus omega, like that. And let is a positive operator in Banach space and some condition for data. When for the solution of T in these spaces, we have coercive inequality. So I would like all to draw your attention here. No space of faces only formulate in the interpolation spaces here. Note the spaces of smooth functions, this in which coercive stability has been established dependent on the parameter alpha, beta, gamma. However, the constants in the coercive inequality depended on alpha. Hence, we can choose the parameter beta and gamma freely, which increase the number of function spaces in which non-local boundary problem 2 is well posed. In particular, theorem 3.5 implies the well-posedness theorem 3.3 in C of E alpha established in the above. Moreover, choosing alpha beta beta equal gamma, we get the following theorem on well-posedness of the non-local boundary problem 2 in C alpha alpha E. Suppose some condition for satisfied for given data, then boundary problem well posed in this norm, and A is a positive operator in Banach space. For the solution of T, we have the following coercive inequality for this problem. Note that well-posedness non-local boundary problem in the Hilbert space with weight alpha alpha was established for the first time by Samarskii in 98. This paper. I would like to draw your attention here. We have condition A phi from E and C also phi. Here, not necessary smoothness property for given data phi and C. So now applications. Finally, we consider application of theorem 3.1, 3.2, and 3.6 for elliptic equations. First, we consider non-local boundary problem for two-dimensional elliptic equations. So this is a two-dimensional case, and here two type condition. One in Samarskii with respect to one variable, other variable non-local conditions. And here for smooth data and functions, and also if we have compatibility condition, our problem has smooth solution. Also some condition for coefficients, positive and non-local conditions, and we can formulate now. We can consider this problem as abstract problem, and we can formulate here what we get from our abstract theorem. So first, we introduce here Hölder space functions where is such type norm finite. C01 normally all continuous function defined at 0, and it is well known that differential expansion 18 define positive operator A acting in Hölder space with domain C beta plus 2 L satisfying the non-local conditions. So we can transform now our problem as abstract problem. Now using results, we can formulate two types of results. One assumes that 90 condition satisfied, then we have such type coercive inequality. And theorem 4.2, if satisfied 20 and 21, we have also two type coercive inequality results. Second, we consider non-local boundary problem, two-dimensional elliptic equation. Here, both for both variables, we have here Samarskii Ionkin conditions, and now we put all smoothness conditions and compatibility conditions for the our solution, and AX must be positive. And we will now introduce differential operator, and differential operator defined 3.1 and acting from Hölder space to C beta 2, satisfying the condition, Samarskii condition. Therefore, we can replace boundary problem 2.22 or abstract problem 2, and using results 3 and 3.1 and 3.7, we obtain here two type results. Assume that first smooth data condition satisfied, then we have coercive inequality, such type coercive inequality. And if we put condition 24, 26, we get results like that. Why we put 25 equals 0? Because we have positivity property, such type operator, but later we will consider structure interpolation space. Until today, no, ready. If we have structure interpolation space, we can formulate full, maybe, results. Third, we consider non-local boundary problem for two-dimensional elliptic equation with involution in X. And here also some smoothness conditions, and for coefficients more now condition because arising from involution here. So we can formulate here results when satisfied 27. We have coercive inequality. The proof of theorem 4.5 is based on abstract theorem, self-adjointness and positivity in L2 minus LL of the differential operator, defined by formula 20A with domain. The A, this is Sobolev spaces, and where minus L, where L equals 0. First time we study such type problem with joint with some Sarsanbai from Chimkent. And theorem 4.6 assumes that 29 and 30 conditions satisfied. Then we have such type coercive inequality. Here also 0, because also not ready structure interpolation spaces with involution. So maybe in future we will study these problems. The problem 39 is based on abstract theorem 31 and self-adjoints and positivity L2 minus L differential operator defined by formula 28. First, let omega in the unit open cube in the n-dimensional Euclidean space with boundary S and omega coupler equal union S in the 0T omega. Consider mixed boundary problem, multidimensional elliptic problem. And here, two variables, y and x. Really, we will consider specific type of elliptic problem. And so if we have smoothness condition and compatibility condition and positivity condition for coefficients, we have here problem where we have exact solutions. And we introduce here Banach space, continuous functions in Hölder space with indicator, with weight, two-type weight, with occupied there with norm. And C, omega is a space of continuous functions occupied with maximum norms. It is well known that differential expression defines a positive operator AX on C beta with domain of AX subset of C0 2 plus omega of M omega and satisfying the boundary condition y equal 0 on the S. Therefore, we can replace boundary problem 31 by the abstract problem, and using results 31, 36, we can obtain two-type results. Let us satisfy 33 when we get such type results. And 34, 35, we get also similarly results like that. And a last case, maybe full case, when we will consider, we consider non-local boundary problem on the range, y from 0 to t, x from Rn, and for 2M the multidimensional elliptic equations. So under the smoothness and compatibility condition, we have here also, we need some condition for coefficients. So we need to define it here symbol bx of c of differential operator of the forms 38 and the acting on the function defined on the space Rn, satisfying the inequality 39. The problem 36 has unique smooth solution. This allows us to reduce boundary problem 36 to the boundary problem 2 in Banach space E Hölder space of the all continuous functions defined on Rn, satisfying and Hölder condition with indicator beta from 0 to 1 with strongly positive operator Ax equal Bx plus delta identity operator defined by 38. Assume that phi and xx from C to beta Rn and right side from Hölder with respect to weight alpha alpha with respect x here beta C beta. Then for solution boundary problem, Korsteff inequality holds. The proof theorem 4.1 is based on the abstract theorem 36, positivity operator Ax C beta Rn, and Korsteff inequality for the elliptic operator Ax in C beta Rn. So we need put here beta strongly greater 0 because C beta it is not true. Beta equals 0 it is not true. So we get such type Korsteff inequality, and next assume that right side from C alpha C beta Rn and satisfied 40 and 31 condition, and we get here now different from first one, other new coercive inequality like that. And proof 4010 is based on abstract theorem, 31, 32, and positivity operator and X in Hölder norm, structure interpolation, functional spaces E alpha generated by square root of A X CRN, and then coercive inequality for the elliptic problem in Hölder space. And now about conclusion and our future plans. Present paper, non-local boundary problem is Samarskii on condition for elliptic equation in Banach space with strongly positive operator investigated. The main theorem of well-posedness of this problem are proved. In practice, coercive inequality estimates for solution 5 type non-local boundary problems with Samarskii on condition for elliptic differential equation are proved. Investigate high-order accuracy for the numerical solution of the non-local boundary problem with Ionkin condition elliptic differential equation. This is our future plans, but as you see here, our differential equation, but problem involves operator A, but our solution involves square root of A. And using maybe formula, abstract formula for solution, we can construct it very easy high order accuracy difference schemes because our solution generated by exponential function of operator. But unfortunately, such type difference schemes no chance to applications. Why? Because applications we need constructed different some algorithm in computer, but structure of algorithm square root of A in the case of matrix also not easy problem. So here problem visualization, but we have some techniques for solving such type problem for non-local problem, and I think it is maybe useful here also. So next problem when high order derivative small parameter investigation uniform two-step difference schemes and asymptotic form for solution of non-local boundary perturbation problems, Samarskii Ionkin condition, linear elliptic equation Banach space with positive operator n and with epsilon parameter multiplying high order derivative term. It is also a problem for us, construction uniformly difference schemes and construction asymptotic formula for the solution. It is maybe a future plans also. So this is end, but how many time I have, maybe. Okay, but here I said why I consider here not E but some interpolation space A alpha, because here different type of results. First, abstract results. I need some maybe connection between some results, other results, because all these results in the spaces of smooth functions with respect one variable and with respect other variables. And if C alpha, that means simpler case, maybe maximum norm with respect one y variables and for example, Hölder norms other variables. But if Hölder with weight also nice, you can maybe sometimes you can choose maximum norms. But here some relation. We can choose both one. Why? Motivation maybe starting point. Why I studied Sobolevsky first time? He drew his attention for such type problem because when he studied long time with Navier-Stokes, he needs some good estimate coercive inequality for the parabolic problem, but it is degree not connected, not like alpha plus 2, for example, may be different. So first paper published in 74 for parabolic problem. After that 69, all concepts depended with his study Navier-Stokes. So why we study later such type problem? Because it was basic our study problem with stability, Kranka-Nicolson's differential scheme for parabolic equation. Here also we need consider here our concepts interpolation spaces. Why? Because sometime in Banach space problem with stability Kranka-Nicolson differential schemes. So it was starting point from differential schemes. After that, we will consider our problem in the partial differential equations. So this is the end of my...
Let us then, давайте поблагодарим профессора Ашyralyeва за замечательный доклад. Пожалуйста, вопросы на любом языке. Замечания? Пожалуйста, Александр Леонидович.
Я хотел сделать одно только историческое небольшое замечание. Значит, на самом деле мы с профессором Ашyralyeвым познакомились значительно раньше, еще в конце 90-х, заочно. В наших исследованиях параболических дифференциально-радостных уравнениях мы использовали существенные результаты, которые мы больше нигде не могли найти, из совместной монографии Ashyralyev и Samarskii. Точное описание в случае гильбертовых пространств, пространства начальных данных для абстрактных параболических уравнений. Я думаю, вы помните, по-моему, даже глава 2, я помню.
Да.
Вот, так что нам это очень оказалось полезным. А потом уже, естественно, когда предоставилась возможность нам лично познакомиться, мы быстро нашли общий язык. Так что вот, как всегда в научном мире, первичным оказывается общий научный интерес. Так что спасибо вам большое за вот те результаты, которые уже давным-давно были опубликованы, которые очень, так сказать, помогли нам в свое время.
Хорошо, спасибо.
Спасибо, Александр Леонидович. Еще замечания? Тогда давайте еще раз поблагодарим профессора Ашyralyeва. На этом утреннее заседание закончено. Продолжим в 15 часов. Здесь же.